In this next section, we'll take a look at some trigonometrical problems involving three-dimensional situations. So let's take a look at this question. Here we're told a glass roof lantern is in the shape of a pyramid and it has a rectangular base CDEF, and at its apex is a point B. The vertical height of the pyramid is given as AB, where A is the point of intersection between the diagonals at the base of the lantern. And we're also told that CD is 2.5 meters and CF is 3 meters. And we're asked to show that the length AC is equal to 1.95. Now, many three-dimensional trigonometrical problems involves taking out right-angle triangles from the model and solving these triangles. So here we have a diagram that shows the pyramid. You can see it has 4 sides, and the sides of the base are 3 and 2.5, and we're trying to get this length AC. So you can see that AC is the diagonal of this triangle at the base. So if we get this distance CE and divide it by 2, we can get the distance AC. So this distance here is also 3, so we could say CE squared is equal to 3 squared plus 2.5 squared, which is 15.25. So CE is the square root of 15.25, which is 3.905. So therefore AC will be half this distance, which is 1.95. In part 2, we're told that the angle of elevation of B from C is 50 degrees. In other words, the angle BCA is 50 degrees, and we have to show that AB is 2.3 meters. So consider the right angle triangle CAB. We're told that the angle of elevation of B from C is 50 degrees. So this angle here is 50 degrees. And we are looking for AB, the length AB, which is the vertical height here. So once again, let's take this right angle triangle out. So here we have it. And we're looking for the length AB. So we can use tangent. Tan of 50 is the opposite over adjacent, which is AB over 1.95. So therefore, 1.95 times tan 50 is AB, which is 2.3 meters. In part 3, we're asked to find the length BC correct to the nearest meter. So once again, let's focus on the right angle triangle ABC. We have 1.95 from part 1. We have 2.3 from part 2. So if we take this right angle triangle out, we have we can use Pythagoras. So we could say BC squared equals 2.3 squared plus 1.95 squared, which is 9.09. So BC is the square root of 9.09 to the nearest meter is going to be 3 meters. In part 4, we're asked to find the angle BCD to the nearest degree. So we're looking for the angle BCD. So let's take this triangle BCD out of the 3D model, and we have it here in red. We have the 2 side lengths 3 meters and the base is 2.5 meters. Now we're looking for the angle C, so you could actually draw a vertical line down from B to the base, divide 2.5 by 2 and use the cosine adjacent over hypotenuse to get the angle. Or you could use the cosine rule, which is what I've done here. And remember, for the cosine rule, you're interested in the angle and the side opposite. So we have the side opposite the angle, it's 3. So we can say the side opposite squared, 3 squared, is equal to the sum of the other 2 sides, b squared plus c squared, 3 squared plus 2.5 squared, plus twice 3 by 2.5 times the cos of the angle between them. So this will give us the following expression, and if we simplify this, we'll get 15 cos of c is 6.25, or cos of c equals 5 over 12, or c equals inverse cos of 5 over 12, which is 65 degrees. So the angle C here is 65 degrees. In part 5, we're asked to find the area of the glass required to glaze all 4 triangular sides of the pyramid. So the lantern is made up of 4 triangles. The front and the back are isosceles triangles, and the sides are equilateral triangles. So the area of the total area of the glass will be twice the area of the two isosceles triangles plus twice the area of the two equilateral triangles. And then to get the area of any triangle, it's half AB times the angle between, sine of the angle between A and B. So if we look at the triangle BCD, first of all, we worked out this angle of 65 degrees earlier. So the two angles at the base will be 65. So 65 and 65 is 130. 130 from 180 gives us 50 degrees. So this angle up here is 50 degrees. So the equilateral triangles will have an angle of 60 degrees at each of the vertices. So we could say the total area will be twice. So for the isosceles triangles, it will be twice the area of one triangle, which will be half 3 by 2.5 times the angle sine times the sine of the angle of 65 degrees. And for the equilateral triangles, it'll be twice half 3 by 3 times the angle between the two sides, which is the sine of the angle between the two sides, which is sine of 60. So if we work this out, we get 6.79 plus 7.79, which is 14.58, and to the nearest square meter, it's going to be 15 meters squared. Finally, in part B, we're told that another roof lantern in the shape of a pyramid has a square base CDEF. The vertical height AB is 3 meters, where A is the point of intersection of the diagonals of the base as shown. The angle of elevation of B from C is 60 degrees, and we're asked to find the length of the side of the square base of the lantern, and to give our answer in the form the square root of A meters. So let's put in the information we're given. We have the vertical height AB, which is 3 meters. We have the angle of elevation here, which is 60 degrees, and we're looking for the side lengths of the base here. We're looking for X. So if we look at this if we take this triangle out, the triangle ABC as before, we have a right angle triangle, and we could say that tan of 60 is the opposite over the adjacent, which is 3 over CA. So that means CA is 3 over tan 60, which, if you work this out, is 3 over root 3. And if we multiply above and below by root 3, this works out to be root 3. So the distance CA is root 3. So the distance CE will be twice that length, which will be twice or 2 times root 3. So now we could look at the triangle CDE at the base of the lantern, and we could say the hypotenuse squared, CE squared, is equal to the sum of the other two sides squared. So we can write CE squared equals x squared plus x squared. But we know what CE is, it's 2 root 3. So we have 2 root 3 squared equals x squared plus x squared, which means that 2x squared equals 2 root 3 squared. And 2 root 3 squared is just 4 times 3. Divide that by 2, we get 12 over 2, which is 6. So x is the square root of 6. Now here's a question you could try yourself. It's question 9 on the 2017 paper. We're told that Connor's property is bounded by the straight bank of a river as shown in figure 1. T here is the base of a vertical tree that is growing near the opposite bank of the river. TE is the height of this tree as shown in figure 2. And from the point C, which is due west of the tree, the angle of elevation of E, the top of the tree, is 60 degrees. And from the point D, which is 15 meters due north of C, the angle of elevation of E is 30 degrees. And we're told that the land on both sides of the river is flat and at the same level. And in part A, we're asked to use the triangle ECT to express the length TE, the height of the tree, in the form of the square root of A times the distance CT. In part B, we're asked to show that TE may also be expressed as root 225 plus CT squared over 3. In part C, we're asked to find the length CT from the base of the tree to the bank of the river at Connor's side. and we have to give this answer to 1 decimal place. In part C, we're asked to find TE, the height of the tree, and again to give the answer correct to 1 decimal place. Now in part E, we're told that the tree falls across the river and hits the bank at Connor's side at the point F, and we're asked to find the maximum size of the angle FTC and give the answer to 1 decimal place. Finally, in part F, we're asked if the tree was equally likely to fall in any direction, find the probability that it would hit the bank at Connor's side when it falls, and give your answer as a percentage correct to 1 decimal place. Here's another 3D question using trigonometry. This time we're told that a regular tetrahedron has 4 faces, each of which is an equilateral triangle. And we're told that a wooden puzzle consists of several pieces that can be assembled to make up a regular tetrahedron. And the manufacturer wants to package the whole assembly in a clear cylindrical container with one face flat against the bottom. And if the length of one of the edges of the tetrahedron is 2a, you have to show that the volume of the smallest possible cylindrical container is 8√6/9 times pi a cubed. So have a go at these 2 questions yourself. And if you'd like to see some more sample videos, visit projectmathsrevision.com or email projectmathsrevision@gmail.com.